In this related rates problem, we're going to be looking at an example from physical chemistry where we look at an ideal gas and it's going to be changing its volume or its temperature, and we want to know how other rates are going to be affected by those changes. Here, for those who are less familiar with this equation, we have P, which is pressure. We have V, which is volume of a gas. We have N, which is the amount of gas. In this case, it's the number of moles, which is just a unit of counting in chemistry. And we have R, which is an ideal gas constant. It's something that is measured and recorded for different unit choices. And T is temperature. And the key thing here is in degrees Kelvin. So relative to absolute zero as opposed to degrees Celsius, which would be the normal day-to-day temperature measure. So that is a relationship between quantities that's always true. This is the ideal gas law. Now let's get into the scenario that we're asked to study. We're given a certain amount of gas, 0.1 moles, so we know what N is, and they're being held in a piston. So piston is typically a cylindrical chamber, and then there's some kind of stopper and a pusher on that stopper. And here what's going to happen is we're going to hold the temperature constant at 273 Kelvin, which is 0 degrees Celsius as it turns out, but irrelevant for the calculation. And then we're going to move the piston to decrease the volume. So we're going to push this piston in. So again, if we're trying to draw a few of the scenarios here, we're going to have this piston moving inwards. And they tell us that the initial volume is 3 liters, and it shrinks to 1 liter over 60 seconds. It's not said, but we presume this at a constant speed. So if we go from 3 liters down to 1 liter over 60 seconds, that would give us a change in volume over a change in time of minus 2 liters every 60 seconds, or minus 130 liters per second. But because this rate is constant, we would actually be able to state this as a derivative. So we know how quickly the volume is changing. What's the question we're being asked here? What is the pressure halfway through this process, and at what rate is the pressure changing at this time? So pressure is P equals something, and at what rate is the pressure changing? That's our question. What is dP dt at an instant as this piston is closing down and compressing the air, compressing the gas in this piston? All right. Well, our first step in these problems is to find a relationship between the variables. Here it's volume and P, which we want to relate the rates of, but we already have that. We already have the always true relationship that P times V is equal to nRT. So we can go straight to our process of taking a time derivative of both sides. Now we have a lot more variables running around here, but we're going to see how that plays out. In this particular scenario, it's not going to be as complicated as it might be in others. So the derivative of pressure times volume is going to equal the derivative of N, R, and T. We're going to focus on the right-hand side first. N is equal to 0.1 moles, and so it's constant with time. So the time derivative of N is going to be the same as the time derivative of any constant. R is, by definition, a constant. It is the ideal gas constant. And T, temperature here, might in some scenarios be changing, but here it's constant as well with time. It's constant at 273 Kelvin. Well then, what's the derivative with respect to time of this combination of values? What's the derivative of 0.1 times some number times 273? These are all constants. At the end of the day, we're going to get a big fat zero on the right-hand side. Part of which came from the fact that some of these values are constants, and part of it coming from the fact that some of these variables for this problem were defined to be constants. So that means all the interesting stuff is happening on the left-hand side. Here we're taking the derivative with respect to time of P times V, and notice that this is a product for the first time in our examples, but we can just handle that with the regular product rule. the derivative of p, the first thing with respect to time, is dp dt, times the second, volume unchanged, plus the first, the pressure, times the derivative of the volume with respect to time. That's exactly what dv dt represents. And with that, we can see the related rates of dv dt, which we know, and the rate of pressure change over time, which is what we want. We'll continue this on the next page. So our goal was to determine the rate of change of pressure, which would be bringing the stuff over to the other side, negative p, dv dt, and then we divide through by volume. That would be our relationship. And we actually know, this would be a volume here, we know this derivative value, but we have to hone in on the pressure and the volume. So let's go take a quick look at that. We were told at the halfway point during the compression, or of the piston movement. And if that's the case, the piston was moving from 3 liters down to 1 liters. So at the halfway, we would get volume equals 2 liters, halfway in between those two. So with our volume being 2 liters, we also need to know the pressure. For that, we're going to have to go back to our initial function up here, our relationship, which would be pressure is nRT all over the volume. We know the number of moles is 0.1. We know the volume would be 2 liters. We know the temperature is 273. And anyone in chemistry should have this ideal gas constant somewhere in the back of their minds. Noticing the units that we'll need here, everything is in degrees Kelvin and liters and moles. And the pressure can be actually in any choice we like. My favorite choice for that is 8.31, and the units in that case are kilopascals for pressure and liters for volume, which is what we have. So if we apply that and go through the calculations, we end up with a pressure of 113.43 kilopascals. That was part of the question, which is at the halfway point, what is the pressure? And then what's happening to the pressure value? Well, we can plug all those values in now. 113.43 for our pressure, our volume is 2 liters, and our rate of change of the volume is negative 1/30 liters per second. Calculating all that out gives us a positive value of 1.89 kilopascals per second in the units that we used for our volume derivative. And so the pressure is increasing. We see a positive derivative here at 1.89 kilopascals per second at that halfway moment, and has a pressure of 113 going up by 1.89 each second afterwards. So that's the kind of analysis we can apply to formulas that are extracted from physics or chemistry, and still the same calculus approach works to help us tie in not just the quantities, which are fine, but also how quickly they're changing in a particular scenario.